dynamic characteristics of measurement systems is the response before the value settles. Like we use the example of a bathroom scale where the pin waves back and forth until it settles on a stable value, and that is when you read your measurement system. But we can also describe what happens on its way to stabilizing with dynamic characteristics, and this is quite a heavy topic that automation students spend like half a year studying, but we will just give a short intro to the tools we work with and what decides the dynamic response. When you have dynamic response, you actually have a differential equation that this explains or models the system. So for first order systems, you have a first order differential equation, and for example here, a system, a massless spring and damper. So it would be like this system, if you imagine this system hanging, but there were no mass there at all. Now the mass is the only thing that has the ability to create an overshoot here. Let's see if this animation shows us. So like this one has an overshoot, the waving form here, and the only reason that it has overshoot or waving like that is because it has inertia, treghet in Norwegian, and the inertia comes from the mass here. So if it didn't have a mass, it would simply just go down to and settle at one value. So if I held the spring down here, if it didn't have a mass, then it would just go up to a new value. Then it would be a first order system. Also, for example, thermal systems, if I have a piece of stone or something that has one temperature, let's say that it has 70 degrees, and I take it outside and it's 15 degrees outside, it will gradually drop down to 15 degrees, but it will not overshoot or undershoot. It will just drop down to the new value. Second order systems have a second order differential equation or an element in the equation, and the second order part here is the one that results or may result in an overshoot. Then you have something called a damping factor. It's the Greek zeta here, and you have the oscillation frequency omega n. But this one you have only a tau factor. It's the Greek tau, and that is the time factor. So it's the damping factor as time-wise damping. Examples. For mechanical systems, you have the spring here. The force is linked to the position with force K times the position. If you have a dashpot, that is støytdemper in Norwegian, well then that one would resist velocity. So the faster you try to pull that one or push it into the chamber here, the more it will resist. So if you try to push it very slowly, it really doesn't resist much at all. So this one depends on the first derivative of the position, which is velocity. Then you have the inertia that comes from the mass, where the force is m times a acceleration, and acceleration is actually a second order differential of the position. This is the change of velocity, is the change of position, and acceleration is the change of velocity. So then you have a second order. The same goes with rotational system. rotating systems, you can have a drive shaft with a torsion spring, which is something that resists turning, and you have a rotational dashpot, en roterende støtdemper in Norwegian, which means that it's hard to rotate in this chamber with oil or something. And then you have the moment of inertia with dreiemoment in Norwegian. You have it in electrical systems, where you have a resistor voltage current relationship is linear. It's not a differential equation. But when you have an inductor, well, then the voltage is the first derivative of the current. And if you have a capacitor, the voltage is the first integral of the current. So if you have these three together, you have three different levels of differential equations. You have it in thermal systems. Note that you don't have here a second order differential. You have something called a thermal resistance, and you have thermal capacitance. Thermal resistance is associated with how hard it is to get heat from one point to another, like through an insulated window or something. And thermal capacitance is how much temperature is stored in an object. So if this was a piece of brick, if I added temperature, you could actually get that temperature back a few moments later, because it stores temperature. So it's thermal capacitance. But the thermal resistance is how much it would stop the temperature from going through to the other side. And of course, all objects have a combination of these two. But some have more thermal capacitance than others. They can store more temperature. And some have more resistance than others. If you ever tried to use a silver spoon in a hot cup of tea, then you have discovered that it becomes very, very warm because it conducts heat very well. It has a very low thermal resistance. Pressure systems, you have pressure resistance, pressure capacitance, and you have also pressure inertance, which is bit like inertia, träghet. Now, all of these differential equations, they are really hard to work with. It's a lot of mathematics involved, especially when you have 2 or 3 such systems combined together. So there was fortunately a man called Pierre-Simon Laplace who in the early 1800s discovered a method so we could actually have a workaround on these differential equations. Let's see what we do here with his method. You have an input to something that is described by differential equations, or more commonly actually a set of differential equations. So you have both thermal and electrical, or even hydraulic, combined together, so it becomes a very, very complex differential equation, and it's almost impossible to calculate the output from that. Now, what Laplace did was that he converted this one, the input here, to a new form of input, but now in the S-plane. So what is S? Well, S is one kind of frequency. So he converted the time plane to the frequency plane. He also converted the differential equation, and the differential equations now became polynomials instead. And polynomials, they are quite easy to work with. So what you get from this is that you have your input, it's now working on a polynomial instead, From that you can quite easily calculate an output which is a new polynomial. Well, that would be quite useless unless we could do the inverse conversion again, and now you get the output in a time plane. So you didn't have to go through this mess of differential equations. You convert to frequency plane, but you never but you only use it as a tool. So you use that as a tool in order to work with polynomials instead of differential equations, and then you can do the inverse Laplace transform at the end. And tools like MATLAB, for example, have brilliant tools for working with these Laplace systems instead of working in the differential equation world. So here you have something called a transfer function. You actually develop a transfer function. So that is the function here is what is called a transfer function, because you transfer the input to the output via the transfer function. You transfer via the transfer function. A transfer function, also known as a network function, is a mathematical representation in terms of some kind of frequency of the relation between input and output of a linear time invariant system. Time invariant means that it doesn't change with time. The equations for the system, they are the same for weeks and years. And linear means that you can draw the graph for the function without lifting the pencil from the board. This is what Wikipedia says. ITS, they say that it's a mathematical statement that describes the transfer characteristics of a system, okay, because you transfer the input to the output, or a subsystem or some equipment. It's a relationship between the input and the output, that's a transfer function, of a system or a subsystem. When the transfer function operates on the input, the output is obtained. So when the input works on the transfer function, you get the output. If you know the output and the transfer function, you can actually calculate what kind of input was given to it. And even if you have the input and the output, you can calculate what the transfer function is. So then you have a book by Bolton, Instrumentation and Control Systems, where he said that in general, when we consider inputs and outputs of systems as functions of time, then the relationship between them is given by differential equations. If we have a system composed of two elements in series, with each having its input-output relations described by differential equations, it's not easy to see how the output of the system as a whole is related to its input. What he really says there is that the relation between input and output via a time-based system is a nightmare. It's differential equations, and you have a set of differential equations on top of each other, so it's really a nightmare. There is a way we can overcome this problem, and it's to transform the differential equations into the more convenient form by using the Laplace transform. This form is much more convenient way of describing the relationship than a differential equation, since it can be easily manipulated by the basic rules of algebra. Yes, we can. Polynomials, they use the basic rules of algebra. So you multiply the input with the polynomial and you get the output. And if you had two systems, you simply multiply them by each other. So that's why it's easier. But this course is not a course that will go through the Laplace transform. You should, however, be aware that there is a tool called the Laplace transform, and it's used in order to get rid of these awful differential equations.